HPC system here at the University of Arizona. Let's get into it. So here's our outline for today. We're going to just do a very general HPC overview at the top. Then we're going to talk about system access, the layout of the system, how to store and transfer files to and from the system, what software is available, and then finally, at the very end, we're going to talk about accessing compute, or in other words, how to run your jobs on the HPC. So stick around. The really interesting practical stuff is at the end, but we need all of the context in order to get into it. So what is HPC used for? HPC is used for a number of different things, such as computational chemistry, weather predicting and climate modeling, technology development, biomedical engineering, quantitative finance, logistics, social science, astrophysics, which is my background, and so much more. So let's get into the HPC overview. Why HPC? Well, when you start running your code, you might realize that sometimes it takes a little while to run. And we don't want you to be waiting until you're ready to retire for you to be able to, access your results. So what are the problems that HPC tries to address? If your computation takes too long, well, the solution here is to get a more powerful computer. If the computation is too big, you might want to link multiple computers. And if you have too many computations, you might want to use a separate computer for each job. So what actually is the HPC? What is a high-performance computing system? So it's what we call a cluster, which means that it's a large interconnected system of individual computers that we call nodes. And supercomputer is a commonly used nickname. So rather than a Jaguar in comparison to a, 1980s Honda Civic, I'm not sure exactly what that is, but, if your laptop is a kind of run-of-the-mill car, a supercomputer isn't just a very fancy computer. It's actually more like a fleet of halfway decent computers, right? Rather than one supercharged sports car, we have a fleet of Dodge Chargers, right? So why is that actually helpful? Why don't we have the supercharged computer? Well, part of the reason is that the supercomputer is a shared system. You're using it with many other people. It's not like you're the only one that has access to it. So a laptop is a personal computer and a supercomputer is a shared system. And in addition, the laptop is something that's local. You have it right in front of you. You see the entire computer. If you wanted to take it apart right in front of you, you could. The supercomputer is only accessible remotely. So you have to log in through a handful of different means via your laptop rather than accessing it directly. And the laptop is hands-on. Anytime you interact with the laptop, you get immediate response in terms of what you decided to do. If I open Google Chrome just opens right in front of me. The supercomputer is hands-free. In other words, a large majority of the jobs that are run on the supercomputer are called batch jobs, and they're automatically run, meaning that you tell the computer what to do with something called a batch script, and you tell the computer that you want to run it, and then you walk away and the computer will run it when it has the chance to. So let's clear up some common misconceptions about the HPC or about supercomputers. So one common misconception is that if I have a Python script that I'm running on my laptop and maybe it's taking too long and I want to analyze my data faster and I put it on the HPC. Unfortunately, the answer to this is no. My code will not automatically run faster if I just put it on the HPC and change nothing about it. HPC's power comes from parallelization. So in order to make your code run faster, you need to make sure that your code is actually able to use the parallelization capabilities of the HPC. Another common misconception is all nodes on the supercomputer are the same. So for example, you might say, okay, well, I logged onto the HPC. That means I'm on the supercomputer. That means I can run anything I want to right here on the login node. And we'll cover this in detail later. But for now, don't run computations on the login node. The login node is just a sort of standby area where you can manage your files, but it's not something that's actually intended for large computations. So it's important to be aware of that. Another common misconception is that if I'm running my Python script on one CPU on my computer at home and I send it to the HPC and I give it 16 CPUs, that means it will run in 1/16 the time. Unfortunately, this is not always true. Sometimes it is, but under very specific circumstances. So part of the problem is, does your program know that those CPUs exist? And the other aspect of the problem is that scaling can be complicated. Even if your program is able to access all of the resources of the HPC, it doesn't necessarily mean that the problem will scale perfectly with the number of CPUs. So here are a couple more misconceptions. Number 4 here, I can perform any action on the HPC as I could on my own system. Well, on your own laptop, you are the owner of that laptop and you can do anything you want to it. On the HPC, it's a shared system and you are not root. Root here means basically a system administrator type position. So you can't go accessing files that don't belong to you. You can't go installing software in system directories. But other than that, you can do quite a lot of things, but it's important to be aware that there are limitations on the shared system. Another common misconception is, oh, well, if there are restrictions, then I'm not allowed to touch anything. I don't want to mess anything up. Well, you are allowed to install software in your own directories. So part of the problem is that oftentimes when you download software that you want to install, it'll try to go into system directories, and that's not what we want to do. But if you're able to install it in directories that you own, this is perfectly allowed. Yeah, so let's get into the clusters that we have available. So the HPC is in reference to our entire system, and there are 3 different clusters that are available here. So the first one is Puma. This is the most recent cluster. It's the biggest. You don't have to read all of that information on the screen there. The takeaway here is just that Puma is the most recent and the most powerful of our supercomputers. Ocelote is a little bit older, arrived in 2016, and it's just a little bit smaller than Puma, but it's still a great tool. And then lastly is Elgato, the 3rd cluster. This one is the oldest one. Elgato at this point is mostly used for testing or debugging and things like this. However, it is still a great tool with about 130 nodes, each with 16 CPUs. So still quite a lot of resources here in Elgato. So check in. I want to see reactions from you guys. When we say the HPC is more like a fleet of Dodge Chargers than an individual Ferrari, what does that mean? Feel free to unmute yourself and chime in.
Is that where you talked about parallelization?
Exactly, right. So rather than just being able to run one program really, really quickly, the HPC enables you to parallelize. So you can run your program on many Dodge Chargers. There's a point at which this metaphor breaks down, but yes, it has to do with parallelization. Great.
What exactly is parallelization?
Parallelization, so you can imagine, say, a matrix multiplication, right? If I'm multiplying a 10 by 10 matrix, that operation consists of a large number of independent operations. So it would be nice if I could write on a whiteboard right now, but there's a large number of independent operations. So rather than doing them all in a row, you can say, okay, well, operation 10 doesn't depend on operation 4, right? So rather than waiting for operation 4 to complete, I can send operation 10 to another CPU and just have them complete all at once. Does that make sense?
Yeah, thank you.
Of course. And then what's the name of our most advanced HPC cluster? Do you remember what it was called? They were all different cat names. Feel free to chime in or put it in the chat. Puma, yes, that's correct. All right, let's move on. So system access, how do we actually log in to the HPC? So we're here on section number 2. So in order to log into the HPC, just like if you were to log into Facebook or anything else, you need an account first. So there are a few different types of accounts, and we'll talk about them now. So PI/sponsor accounts. These accounts are given mostly to faculty. These accounts enable you to create and own groups. And these accounts also receive the storage and CPU time allocations. Research groups are the most commonly used type of group. This is where you just add your group members, your grad students, your postdocs, etc., to your research group, and then they can access your entire CPU and storage allocation. Another type of group is a class group, and this is intended for, as its name, a class. So if you're teaching a course that uses the HPC, you would create a class group and add your students there because it has limited access to storage and CPU time. And then normal or sponsored accounts. So if you're a student, a postdoc, etc., if you're not a faculty member, you would need this type of account, and you should request sponsorship from your PI. So this enables you to get added to their group. And once you get sponsorship, you can, if you're collaborating with multiple groups, you can get added to other groups around campus as necessary. And you're given access to storage and compute resources according to group membership. And also PIs can join other groups as well. So anybody can join any group provided that the PI wants them to join. And once you're in the group, you have an active HPC account and you can log in. So groups, let's just talk about them a little bit more. Groups are ways to organize users on HPC. Research group membership provides HPC account sponsorship, access to the group owner's full compute allocation, and access to the group owner's full storage allocation. So the compute allocation is what you use to run your jobs, and the storage allocation, of course, is where you can store your data. So again, we'll talk more in detail about these later. And then class groups are intended for a single semester and provide limited access. So how to create your account. If you are a member of the University of Arizona, the first step is to visit the portal. So portal.hpc.arizona.edu. If you just log in there, this will automatically create an HPC account for you. But remember, there's another step, and that's sponsorship. We would go to same URL /portal/send link, and then that will take you to a page that looks like this. Faculty sponsor themselves, so they go to the left-hand box. Non-faculty must request sponsorship, so they put their sponsor email in there, and then that sends an email to the sponsor. They say yes, and you're good to go. If you're not a UA affiliate, you can still get access if you're collaborating with a group here on campus. So you can request status as a designated campus colleague, or DCC. And to do that, you would go to this link here and follow the instructions there. So moving on, once you have created your account and received sponsorship, then you can access the HPC. Okay, so let's just check in here. Give a check mark reaction if you already have an HPC account and you have been sponsored, or give an X mark reaction if you don't have an HPC account yet. Just kind of curious to see what's going on. Very nice. I'm seeing a lot of checks. Unfortunately, I actually can't see everybody, which is weird. I never really know how the Zoom thing works, but I see a handful of check marks, so that's nice. Cool. So we'll maybe, if we have time, we'll maybe go through a short example of submitting a batch job later. So if you have an HPC account and you'd like to follow along, this is something that you could follow along with. Hey, there it is. Thanks, Devin. Okay. All right. So how do we connect to the HPC? There's two main methods to connect to the HPC. The first one is the browser, which provides a graphical user interface. And the second one is the terminal or the command line, which provides quite a lot of control and accessibility, but it also is only text-based. So Open On Demand, that's the name of our browser-based interface. The website is ood.hpc.arizona.edu. You log in there, and you'll have access to the browser-based graphic user portal. So this enables you to do a lot of things, such as, browse your files, go to an interactive desktop, access GUI-based applications, which you see on the right here. So GUI standing for graphical user interface. Also easy access to the terminal. The downside is that it can be a little slow if you're doing a lot of, back and forth between your local computer and the HPC. It can slow down a little bit, but it provides great access to a lot of applications that you wouldn't otherwise have access to via the terminal, such as Mathematica, MATLAB, Jupyter. I know these are all very popular applications, so using OOD is a great way to access them. And if you want really fine control over certain things, then OOD, you might need to supplement that by using the terminal on occasion. And then here are the pinned apps. These are some of our most popular apps, such as ANSYS, Mathematica, MATLAB. These are all available for you to use on Open On Demand. And here is a screenshot of the interactive desktop. And this enables you to use the desktop on the HPC just like you would on a normal computer. Click and drag files, move them around just as you would on any other desktop. And if you want to access the shell, it's also possible to grab a terminal by going to clusters at the top, clicking shell access, and then you'll see this black box here where you can type in commands there. So one thing I want to point out here, and again, we'll talk about this in more detail later, but if you see your username at Genonia, this means that you're on a login. So just because you click shell access, again, doesn't necessarily mean that you have access to all of the compute nodes. Make sure to request a job, as we'll discuss later, before running a computation. Okay, so command line access. Why do we want to access via command line when we have that great browser interface over there? So one thing is that it's faster. You don't need to waste your bandwidth on the visuals. You have more control with the use of bash commands. You can write and edit code directly in the terminal using a text editor like Vim or Nano. You can manually access the compute nodes and load software and have sort of an interactive type of session. You can submit batch jobs. And there's no need to babysit your session. On Open On Demand, you might need to keep your browser window open in order to make sure that things are running the way that you want them to. But when you submit a batch job, there's no need to babysit your session. A downside, if you've never used a terminal before, it's a slightly steeper learning curve in order to get a handle of all of the different commands, but hopefully it's not too bad, and it will provide you access to being a more powerful user in the long run. So what is the command line? It's a text-only interface. It is available on any operating system, Mac, Windows, or Linux, and it uses something called a scripting language. So on Windows, the command line uses PowerShell. On Mac and Linux, it uses Bash or ZSH, depending on the version of things that you're using. And Windows also does provide a bash shell now. Windows has something called Linux Subsystem for Windows. So if you'd like to use a bash shell, you can look into that. And that will enable you to use bash commands on a Windows machine. So in order to connect to the HPC, the terminal doesn't automatically connect you to the HPC. It's just a method of inputting commands on your local computer. But one command that will connect you to the HPC is something called SSH, or Secure Shell. And you can access a terminal through Open On Demand, but it's also a program that runs on your personal computer. So it's important to just be aware of what the terminal is. So Bash and Linux, it's important to talk about this real quick. The HPC runs a version of Linux called CentOS 7. this is the operating system you're using on the HPC, regardless of how you access it. So if I'm using a Windows laptop, once I'm on the HPC, I'm no longer on Windows, I'm on a Linux machine because the HPC is running Linux. And remember that you're remotely accessing a different computer. So just because a file exists on your local computer doesn't necessarily mean that it will exist on the HPC. You'll have to go through a transfer method, as we'll talk about later. So the file system and installed software will be different, and the HPC uses bash commands to manage files, navigate between directories, and a million other things. So this isn't going to be a course in bash. There are plenty of really great tutorials and resources online for you to learn bash if that's something you would like to do. So we're just going to really go through only the basics that we need. So what are we actually doing when we're SSHing onto the HPC? Well, this is an overview of what the HPC looks like. So when we see that users on the left-hand side here are connecting to the HPC, they're connecting to this thing called the Bastion host. And we'll go through these nodes in more detail later, but it's important to just have this mental picture of what's going on with the HPC in your mind, because the HPC, while it's one system, it is not necessarily one computer. There are many, many, many different computers that are involved in creating the HPC experience. And the secure shell enables you to connect your computer locally, your laptop, by sending cryptographic information to the SSH server, which enables you to access the HPC. So we'll just skip this for now. So once you're logged into the HPC, there are different clusters, and I just want to show you here the prompt on the bottom left here. You see my username at Wenteltrap, so that's another name for one of the login nodes. You see they're both of the names there. So just be aware that when you log into the HPC, you don't want to just start running programs left and right. You want to use the techniques that we'll talk about today. So once you see the prompt with a login node, you're in. What can you do? So you can use bash commands to manage files. You can install code or software you need for your research. If you need to compile things, make sure to do that on a compute node, not onto the login node, because that can stress the system. You can use an interactive session for testing, so we'll talk about interactive sessions later on. And you can submit a batch job. So these are different ways of running your code on the HPC. And here are a handful of useful commands that you can use. So these are not strictly bash commands. These are system utilities that our team has input that enable you to do a handful of different things. So if you need to switch your cluster, you just type the name of it. If you want to see how busy the HPC system is, just type nodes busy, and that'll give you a graphical overview of how busy the system is. So if you submit a job and you're like, hey, why is that not running yet? You can use nodes busy to see, oh, well, the system is really busy, so it might take a little while. You can get a summary of your storage usage using the command uquota. You can use VA, which stands for view allocation, to see how much compute time you have left, and so on and so forth. So one thing that might make access to the HPC a little easier is this thing called SSH keys. So we have instructions in our documentation, so I won't go through it all in complete detail. So in order to create an SSH key, you create a private and public key pair, and then you put that onto the HPC in order to reduce the number of times you need to enter your password. And the reason you might want to do this is because if you fail a password check 3 times in a row, then it will lock your account for 1 hour, and there's nothing we can do about it. But it's only 1 hour, so wait for that to finish, and then you'll have access to the HPC again. So you can't avoid this with SSH keys. So it's important to have a secure password. But a secure password also means that it might be a pain to type. So SSH keys are a way to solve this problem. And instructions in our docs or on Google. So check in real quick. What are one pro and one con of using the Open On-Demand interface? Feel free to type it in the chat or to say it out loud.
Well, it could be slower when you are like moving between your personal PC, your PC and the HPC sometimes.
And that would be a pro or a con?
a con.
Yeah, exactly. Pro, graphics, con, slower. Exactly. So how about one pro and one con of using the terminal? Yeah, exactly. So one pro could be more options and more flexibility. A con could be more technical or maybe a steeper learning curve. Yeah, terminal opens up more options for batch submissions as well. And one other con that I'd like to throw in there is that you don't have access to graphical applications like MATLAB or Jupyter Notebooks, right? So it's important to just understand what the two options are for and what your preferred use case is and which one you can get most out of depending on your own needs. All right. So let's talk about the system layout. So now we're going to talk about the nodes a little bit more. So we're here in section 3, system layout. So the very broad overview of the architecture of a supercomputer is that you have these sort of individual computers called nodes. Each node has CPUs and cores and shared memory, and all of those nodes are interconnected together, and they all can access a shared file system. So, if I'm on node 47, this has access to the same file system as node 93, right? They all can access the same files, but they do have their own set of CPUs and local memory. And just as a note of terminology, when I say memory here, I'm usually referring to RAM or the memory that's accessible to the CPU as it's running. If you run out of RAM, then your computer freezes. I'm not necessarily talking about storage space. If I'm referring to storage space, I'll try to say storage space or disk space. So just as a note of terminology there to make it clear. And here's the overview of the HPC system architecture. We saw this before. So there's a handful of different nodes. We'll talk about all of them in detail now. So just to kind of look graphically at this, let's go through it. We have our users. The users connect directly to the Bastion host. We'll talk about what that is in a moment. The login node then connects to the shared data storage. You can notice here that the Bastion host does not connect to anything other than the login node. And that's intentional. The login node does connect to the compute nodes. So if you want to run your jobs, you want to go from the login node to the compute nodes. And then also down here at the bottom, we have this thing called the file transfer node. So let's get into it. So let's talk about the Bastion host first. The Bastion host is a security feature. Host name is gatekeeper. So if you look at your prompt after you've SSH'd in, it will say your username at gatekeeper. That's a good way to note that you're on the Bastion host. There is no file storage on the Bastion host. There's very limited things here. So if you try to put files on the Bastion host, you may run out of space soon. And if you do run out of space, that can cause issues logging in. So just try not to do really anything at all on the Bastion host. There's also no compute, so please don't try to run any programs on the Bastion host. Basically, the only thing to do here is to type the word shell in order to access the login nodes. So whenever you SSH onto the HPC, there are sometimes messages here. It is important to read those. When you first SSH onto the HPC, it'll say this is a Bastion host used to access the rest of the RT HPC environment. Type shell to access the job submission hosts for all environments. So that means you want to type shell. Once you've done that, you'll access the login node. Oh, it looks like, oh, yeah. One more thing about the Bastion host is if you do want to bypass it so you don't have to type shell every time, it is possible to do that with something called a SSH jump. So you can use the -J flag after SSHing in order to access the remote server. So in this case, you would put the jump server first and the remote server second. So to do the full command for you, it would be SSH-J, your username at hpc.arizona.edu, and that there is the Bastion host. And then the slash just indicates that it's a continued of the same line. And then you would do user at shell. So the second one shell.hpc.arizona.edu. And that would enable you to effectively log on to the Bastion host and then immediately jump onto the shell or the login node. So that's one way to make that access a little bit more straightforward. Or if you want, you can use SSH files, SSH config files to save host names and proxy jumps. I have this all set up on mine so that I never have to input my password or deal with the Bastion host, and makes it a lot faster to access the HPC. So, you know, there's gonna be a lot of things I'm touching on here that I'm not going to be able to describe in full detail. So I'll say here, if you're interested in SSH configs, there's plenty of resources on the internet to help you get set up with those. And this method pairs nicely with SSH keys. So if I have a jump and I have an SSH key, then all I have to do is type the command and boom, I'm right on the HPC. Very quick, very easy. Okay, with that out of the way, login nodes. Login nodes are where you'll probably spend a large amount of time on the HPC. So this enables you to do file management and job submission, both of which are very important as an HPC user. The host names, as we described before, Junonia and Wenteltrap. And as a side note, does anybody know what those words are? They're kind of weird, obscure words. If you know what they are, go ahead and type them in the chat. And the domain here is shell.hpc.arizona.edu. Nope, it's not a Monty Python reference. I'll give you a hint. Shell, right? If you can figure that out, I'll give you a high five. I don't know. Not quite a turt. I'll just leave that hanging and see if we can figure it out by the end. And the main thing to do on the, excuse me, my ad block has been updated. Cool. Sorry about that. Okay, so accessing the main HPC file system. So you see that this login node here has a connection to the shared data storage down here. And that shared data storage is the main HPC file system, which has shares that begin with /home, /groups, and /xdisk. So once we get to the storage section, we'll talk about that more. Yes, cat, snails. Those names are sea snails, Junonia and Wenteltrap. You should Google them. They're very pretty. In addition to accessing the main HPC file system, you can submit interactive or batch jobs to access the compute nodes. And again, more details on that coming. Important, again, I've mentioned it a handful of times. I'll mention it again. No compute on the login nodes. Don't try to run Python. Don't try to run anything on the login node other than text editor, moving files around, basic bash commands. Okay, so the compute nodes, these are the workhorses of the HPC. This is where you'll get all of your research computing done. And it's only accessible via job request. So the PI's CPU time allocation to pay, I'm using pay in quotation marks because the allocation itself is free. And again, we'll talk about that detail later. On the standard partition, the allocation itself is free. So once you have submitted a job request, you can pay out from the allocation from the CPU time allocation. It is also possible to use Windfall. This is another partition to run preemptible but free jobs. Preemptible here meaning that a standard job can come along and kick you off of the compute node. So if you're okay with that happening, if you have a way of saving your work part of the way through, then it is possible to use Windfall to run jobs that don't subtract their time from the PI's allocation. And interactive sessions provide shell access. So rather than having a script automatically run, you can use an interactive session to have a typical terminal session where you go back and forth. You type a command, you see the output. And batch jobs enable remote automatic running of scripts. So if you know exactly what you need to do, you can write it into a batch job and send it off. So file transfer node, this is the last of the nodes. And as its name suggests, you can use it to transfer files. So the domain here is fileexfer.hpc.arizona.edu. You can SSH onto this node via the login node if you need to. So from a login node, you would type this command and enter your password, and you would be on the file transfer node. And it can be used to transfer files from external machines. And it can also be used to access the rental file system. So the rental file system is additional storage that's available on the HPC that is not on the main file system. So the main file system here you can see is connected to the compute nodes. That means that if I'm running a program, I can access this data from the compute nodes. Whereas on the rental file system, this is not connected to the compute nodes, meaning that I'll need to access it only from the file transfer node. I hope that makes sense. So let's do a quick check-in. Which type of node has access to the main file system, but should not be used to run jobs? The login node, that's correct. So I see one answer for the Bastion host. The Bastion host does not have access to the main file system. You're correct in that it should not be used to run jobs, but the Bastion host does not have access to the main file system. Also, the file transfer node, that's correct. Good catch there. I didn't actually think of that one. So appreciate that. The login node and the file transfer node. And which type of node should be used when uploading data to the HPC? This, of course, is the file transfer node. Okay. Give me one moment. I'll be back in 10 seconds.
I wish this is a place where you could have those intermission music.
Yeah. Yeah, sorry, just gardener outside wanted to close the window, so no distractions. Okay. Storage and transfers is our next section. So please do not try to download the entire internet onto the HPC. We do have a lot of storage, but not quite enough for the entire internet. Okay, so HPC storage resources. What do we have? The high performance storage system. This is the main file storage system on the HPC. So that means it's fast. Copy times between different locations in the main file system tend to be very, very quick. Each user gets a directory under home where they have 50 gigabytes to do what they please with. Each PI gets a share under groups where they have 500 gigabytes, and this is shared between all group members. So each group member should get their own personal folder within the PI's group share, and that 500 gigabytes is, available to everybody. And in addition, if you need more space, PIs can request X disk, which goes up to 20 terabytes. And while home and groups are persistent, meaning that they never go away, X disk does have a time limit of 300 days, meaning that you need to be aware of backing up your files elsewhere if you need to save them as the time comes to the expiration date. So that's just something to be aware of, and you'll get a million emails about that. So just pay attention and you hopefully won't lose any data. Rental storage. PIs can purchase rental storage in rental, and this is persistent, so it's a good way to supplement the main HPC system if you have a large amount of data. It's mounted to the file transfer node, which means that it must be copied to the HPC file system in order to be accessible to the compute nodes. Remember that diagram that we had back there? I won't go all the way back. A couple additional storage options that we have, RDAS, which stands for Research Desktop Attached Storage. This is a great tool, but it is not technically on the HPC. So if you need to move, if you need RDAS data to be accessible to the HPC, it needs to be copied onto it. And you can get up to 5 terabytes of RDAS storage. And the intended use case for this is to mount the RDAS storage to a workstation. So this will enable all members of the lab to access the RDAS station, or sorry, the RDAS share from any workstation where it is mounted. And of course, it can be copied to the HPC. And then we have long-term backup options for archival data, again, not directly on the HPC, through Amazon Web Services. So those are our storage options. Hopefully these seem useful to you and you can find something to do with them. So one quick thing before we move on with storage is file permissions. It's important to note that we are on a shared system. So if all of the permissions were free and open, that means I could go mess around with anybody's files on the HPC, and we don't want that. So these are especially important on a shared system. You don't want anybody intentionally or accidentally messing with your files. So if you want to see the file permissions, you can use the -L option when you use the command ls. So ls lists the files in your current directory. -L means long. H means human readable, so it'll put storage quantities with like K and M abbreviations so that you can see kilobytes, megabytes, gigabytes, etc. And A means archival, preserving original information. And if you want to see permissions on Open On Demand, you would click this box that says Show Owner and Mode. And again, file permissions is one of those topics that goes surprisingly deep, so we're not going to get all details of that out of the way here, but it's something that I want you to be aware of so that if it comes up, you can find the relevant information. And of course, we do have information on file permissions in our documentation. So here's a screenshot of my terminal where I have run the command ls-lha, and you can see a handful of files and folders within that test directory there. So we'll go through each of them, and I have color coded them for ease here because it can be a little bit difficult to parse this if you've never seen it before. And I have a legend on the right side here. So R refers to the read file permission. That just means that you can see a file and its contents. Write file permission, meaning that you can edit it. You can open up a file and change its contents. And the X refers to execute or running a program. So if the program is an executable, this refers to your permission to execute it or to not execute it. So starting from the left, the red column there refers to the item type. So you can see the dash refers to regular files and the D refers to directories or folders. The blue column here refers to the file permission set of the user or the owner of that folder. So for me, all of these are owned by me, meaning that this blue column here refers to my permissions as owner of that file. So you can see for most of them, I have full permissions, read, write, and X, except for the top one where I don't have execute permissions. But that's fine because that file is not an executable, so why does it need execute permissions? Second column here is the group, and the group here is staff. You might see something different on yours, so this would probably be your PI's NetID or maybe something different. And this refers to the permissions that all members of that group have for those folders. So in my case, anybody who's in that staff group can read or execute the bottom 3, but they don't have write permissions. And then folder 1, as you see there, there's 3 dashes in that region. And that refers to the fact that nobody can do anything to that file. They don't even see that it exists. And then read on file 1 there. And then the last column here, green, refers to others. So that refers to any user of the HPC who is not you and who is not in your group. So typically these permissions are closed. Sometimes there might be a good reason to open them up, but in general, those permissions stay closed. And that's the overview of file permissions. Okay. So let's talk about transferring data now. Now that we've seen what the storage options are, where you can move things, let's talk about how to move files from your local computer or from somewhere else onto the HPC. So on Open On Demand, we would, of course, navigate to ood.hpc.arizona.edu, then click Files from the top bar and click the share that you want to access. So you'll click Files and then click one of those three options, depending on which one that you want to access. And you can change it once you've clicked it as well. And here you have the interface. So I clicked the Groups tab, so you can see on the left there, the Groups is highlighted. And I have the ability to do a handful of things: upload, download files, create directories, create files, and do anything that you would need to do in a file browser. There is one limitation though. In Open On Demand, the maximum upload size is 64 megabytes. So if you need to put a file on the HPC that is larger than 64 megabytes, we'll need to use a different option. Okay, so here are the recommended options for different file sizes. So transfers less than 64 megabytes. The web portal offers the most intuitive method. For transfers less than 100 gigabytes, so we recommend using command line utilities such as SFTP, SCP, or rsync. And again, these are commands that have a wealth of information about them, so we're not going to be able to talk about them all in super detail, but just know that they exist and look up their man pages if you want to find their exact syntax. And of course, we would use the file transfer node, so filexfer.hpc.arizona.edu, in order to transfer those files onto the HPC. And for transfers greater than 100 gigabytes, so these are very large transfers or transfers to file systems that exist outside of the university, we recommend using Globus. So these ones here, these are command line utilities, and Globus here is a graphical application. And we have instructions on how to use Globus in our documentation, but for now, we'll say, let's move on. So rsync example. So typical rsync example would be you type the command rsync, you type your options. I'll describe those options in a moment. First, you would type your path to the local file, and then on the same line, I'm just putting it on the next line for space here. You would put your username. Don't forget filexfer, hpc.arizona.edu, and then path to the destination. Note that the source path is first and the destination path is second. And your remote host will always have user with the @ symbol and server. So whether you're taking something from the HPC to your local computer or from your local computer to the HPC, wherever the HPC is, don't forget that it needs this @ symbol in order to indicate that it is a remote host. And the options that I've put in there, R stands for recursive, meaning including folders. V stands for verbose, printing information. And A stands for archive mode, which means preserving item information from the source. So that's just the options that I use. And that's just a simple example for rsync to upload to the HPC. So one of the main things here, don't forget that you need to include file transfer or filexfer rather in the domain name of the remote server. So there are tons of options for transferring data. We have instructions in our documentation for all of them. Go to that URL to find it. And please check there for the details on your method of choice. There are very numerous different methods. And for now, let's move on to software. So we're on section 5 now, closing in. All right, so we've covered the different types of nodes on the HPC. We've covered how to get your files onto the HPC. Now let's talk about what software is available for you to use on the HPC, or how do you interact with software on the HPC. So the availability of software does depend on the node that you're on. So the login node has bash commands, system utilities, and basic functions. It also has Slurm commands. All of the Slurm commands start with the letter S. So SQ, SBatch, SControl, there's a large number of them. We'll talk about those a little bit more when we talk about running jobs. The file transfer node or the data transfer node, there are some limitations to the software that's available here. So if you do run into any funky things happening on the file transfer node, just let us know and we'll take a look. The compute nodes are really where the majority of the software is. So if you're looking to load software using the module command, that's only available on a compute node. If you try to module load from a login node, it's not going to work. And the module command is used to access the full suite of installed software on the HPC. So let's talk about the module commands. When you're on a compute node, the module command are available to help you access the software that you need. So the typical usage is you type module, you type the name of the command that you want to use, and then you type any arguments that you might want to pass to it. So let's go through a handful of commonly used ones. Module avail is used to list the installed software. So if I wanted to list all of the installed software on the entire HPC, I could just use module avail. But say, for example, I wanted to find out which versions of Python were installed. I could do module avail and then put a search term Python in order to print all of the different versions of Python. So you can put search terms there and it will print a list of all of the installed software that matches that search term. Module load, this will load that module. And effectively what that means is adding the paths to that software to your environment variable, which is called path, which enables you to access software. So by loading the module, it will become available to you. And of course, you'll need to tell it which module to load. You can reverse that by doing module unload. Some modules are not compatible with each other. So if you know that module A is not compatible with module B, you might need to unload module B before loading module A. And of course, you can do that in one command as well by using swap. So if I wanted to get rid of module A and load module B, module swap A, B, we'll remove A and add B. If you want to get some more information about that module, you can use module show. And this works for modules that have been loaded. So once I load Python, I can say module show Python, and it will show me all of the paths for that loaded software. And this can be useful if you are maybe compiling your own software and you need to point to some library or something like that. There's a lot of different use cases for this. And then module spider is another way to print versions and other information on a particular module. So these are the most commonly used commands for module, and hopefully they will get you where you need to go. Oh, and module list. Sorry, forgot one. Module list prints the list of all loaded modules. So these are going to be ones that you already have loaded. So if you're loading and unloading modules and you forget which ones you have, use the list command to show the ones that are currently loaded. Okay, so that was all in reference to system software. So modules are installed by the HPC team. If you need something to be installed as a module, let us know. But it is possible for you to also install personal software. So users can't install system modules. However, users can download and compile software within directories that you own. So software should always be compiled using a compute node. So don't compile software on a login node because that can stress the system. So let's run through the brief overview of what that might look like. So I'm just going to use an example from GitHub. So you would, sorry, maybe not GitHub, but from GNU.org. So you would download and unpack your software first. So you would use the command wget, and I've bolded all of the commands here so that hopefully they're easier for you to read. So you put in the URL where your software package is living, you type wget the URL, and then you get it. You unpack it with the tar command, and then you move into that directory. You would configure it by using the configure option, and you would make sure to use the prefix with your home directory there. If you don't use that prefix, it might try to install it into a system directory and you will get errors. So make sure to prefix it into your home. And then you would compile and install it. So the make command, make install, and then modify your environment by exporting the path where you installed that software. And that's the very general overview of how to install a piece of software from the internet. And as another note, I'm realizing I forgot to add a slide on this, so I'll just talk about it. But it is possible to also install software by using a package manager like pip, right? If I'm trying to install a Python package, I can do that in my own personal directories. We don't need to install a different module for each Python package. You can use the pip and Python environments to install modules from their repositories. Similarly with R, you can use the CRAN repository to install packages from their repositories. So double check with your repositories for whichever program that you're using. It might be possible to install those things on your own without doing even this, something even easier. And we do have information about that in our documentation, as well as there's tons of tutorials online how to install packages using pip or CRAN. So definitely check those out if you are a user of a software that has that capability. Okay. And finally, last section here, running jobs on HPC. So this is really the meat and potatoes of what you'll be doing on the HPC. All of the other stuff was really in service of running jobs on the HPC. So accessing compute. How do we access those compute nodes? So in order to access a compute node, you must make something called a resource request. This means specifying how many CPUs you want and for how much time. What type of compute node you want. There are a handful of different types of compute nodes, such as the standard node, the high memory node, or a compute node that has a GPU in it. And important here, just getting this out of the way up top, the number of CPUs that you request determines the memory that you have access to, or RAM, right? In order to make a proper resource request, we need to know what kind of hardware we're working with. So let's go through the hardware that's available on the different clusters. So on Puma, I've highlighted the row here that you'll probably need the most. I will also point out the one above that, CPUs per node. So if you're requesting a number of CPUs and you're only requesting a single node job, make sure not to go beyond that number. So 94 CPUs available on Puma. Each CPU on a standard node has 5 gigabytes. If you want to go to a high memory node, you have 32 gigabytes. And on a GPU node, you also have 5 gigabytes. And on Ocelote, the numbers are different. I'm going to breeze past these because I don't want you to get focused on memorizing them. Just take home the general principle that there are different numbers on the different clusters and that those numbers are available for you in the documentation. So don't necessarily feel like you need to memorize all of those numbers, but just know if I'm on Puma, the value for RAM is going to be different than the value on Ocelote or on Elgato. And all of that is referenceable in our documentation. So let's go over the basics of choosing a cluster. Why would you want to choose one cluster over another one? So Elgato is our oldest cluster. It is, while it's our smallest cluster, it is also not very highly used. So you'll have low wait times on Elgato, meaning that there's just quite a few nodes that are usually open. If you want to hop on an interactive session, Elgato is usually the way to go because you probably won't have to wait. There's fewer resources, so it's good for smaller jobs or for testing. And if you're going to be doing a lot, it is important to be aware that it has the smallest CPU time allocation, so only 7,000 hours on Elgato. Ocelote is our middle child, so it has quite a few more resources than Elgato. And it has many nodes, and there are also GPU nodes that are available. So I realize that that sentence is a little bit ambiguous there. So I don't mean that every node on Ocelote has a GPU, but the ones that do have a GPU have one, and also that's outdated information. We have installed some new GPUs, so some have two. So be aware if this information is in our documentation. It's a great tool. It's a good middle child. You have 100,000 CPU hours on Ocelote. So wait times on Ocelote might be a little bit shorter than on Puma, but Puma is the biggest one, has the newest hardware, has the largest number of CPUs per node available. However, sometimes, depending on usage, the wait times can be long. And, this varies, from week to week, day to day. So sometimes the wait times are going to be lower. Sometimes the wait times are going to be longer. Even if you didn't change anything about your job, you might experience that this week the wait times are longer. And that's just the nature of a shared system. Sometimes it's just in higher demand than others. Let me read this question in the comment here. Installing software in this type of systems can be quite complex, especially when dealing with packages that have numerous dependencies, right? I guess in those cases, we need to request soft package installation. Right. So depending on, this is highly software dependent, right? Some software has a great deal of dependencies and need to make sure to get those right. Whereas other software, if you download it from GitHub, you can install and compile it right there, and then without really having to worry about the dependencies. So it's really highly software dependent. If it does end up being a complicated process where you're not able to figure out what exactly is going on with the dependencies, absolutely, please reach out to us. We are happy to help you either get the software installed for yourself, or if necessary, install it as a module on the system. So we're not necessarily expecting that the users become software engineering experts in order to install software of their own. I'm just pointing out that it is possible to do this, and there are cases in which dealing with dependencies might not be too bad, but in other cases, we're here to help is the takeaway from this. And as Devin mentioned, there's also containers that you can build yourself that handle all of those dependencies for you. And containers are a tutorial in and of themselves. So they're great and they're useful, and there's information on our documentation about how to use them. But let's move on. So note on CPU and memory. I mentioned this before, but each compute node has a certain number of processors that are physically mounted to it. And each of those processors has a memory chip that is physically connected to it. That means that the number of CPUs that you request for your job determines the memory or the RAM that that job has available to it. So the total memory is going to be equal to the memory per CPU times the number of CPUs. So what this means is that memory is not a continuous sliding scale or an arbitrary number. It doesn't mean that you can put in any old value of this and expect it to work exactly as you expect it to. It means that we have to think about the number of processors that we're requesting, the amount of RAM per processor, and then figure out the total memory based on that. And sometimes, different jobs have different limitations. My job might be memory limited. And in that case, I might request more processors than I really need in order to boost the memory that the job has available to it. So it depends on what the needs of the job are. And yes, think RAM, not disk space. Remember that all of the compute nodes have access to the same disk space. So takeaways for memory: know the value of RAM per CPU for your machine, and these values are tabulated online for you. If using the total memory flag, make sure this equals n CPUs times the memory per CPU. And only input allowed values for memory per CPU. So let's talk a little bit about job scheduling and using the Slurm workload manager. So we have a shared system again, many users, many jobs, and a finite number of resources. That means we need to use something called a task scheduler to balance the requirements of all of these hundreds of jobs and make sure that they're all running smoothly. Once your job has been requested, it goes to the scheduler, which places it in the queue according to when it was submitted and the resources that it requested. Jobs requesting more resources or more time will generally take longer to start. And jobs with high time limits will generally take longer to start. Sometimes usage is low and jobs start soon. Sometimes the queue is busy and it takes a while. So it's important to remember that, even if you are experiencing long wait times, that's not necessarily your fault. That could just be a feature of the busyness of the system. And it's not that kind of Slurm, it's this kind of Slurm. Right, so when the system is busy, it might take a long time. So there's a few different ways for submitting jobs. If you're using a graphical job on Open On Demand, you'll want to first select your app from the list and then fill in the resource request form. So that'll be a form on the internet that asks you all of the fields that you'll need to fill in, and you just type in what you want for those, and it basically holds your hand through the whole process. It's not too difficult. Make sure just to select all of the options that you want to choose. And once you submit it, you wait for the scheduler to allocate your resources. So submitting a job on Open On Demand, pretty straightforward. Interactive jobs, we want to use the terminal, again, for interactive jobs. So terminal sessions that allow you to interact with compute resources in real time. That's what an interactive job is. So first step is to use your local machine to SSH into the HPC. Navigate to the login mode by typing shell, and then run the interactive command. So the interactive command, very easy to remember, gives you an interactive session. So an example could be this command. So I type the command interactive -a HPC team -t 4 hours -n16. So without explaining what those options are, can anybody tell me what this is requesting? So it's requesting an interactive session, but what are the parameters that I'm requesting here? Exactly, 4 hours of time, 16 nodes with the account HPC team. So if you were to do this, if you wanted to submit an interactive command, you would replace HPC team with your group. You would replace the time limit with whatever time limit you want, and the number of processors with whichever number of processors that you want. So these are all options that you can pass to it. If you run the interactive command with no options after it, this will still try to give you an interactive session. However, it will do so with the windfall partition. So it means that that interactive session could potentially be canceled at some point if it gets preempted. And it could also mean that it might take a little bit longer to start. Nothing wrong with that if you're okay with those options. But if you do want to use the standard CPU time allocation for your group, this would be the way to do it. And as I mentioned before, interactive jobs, if you try to do an interactive session on Puma, it might take some time to start because Puma is very busy. I recommend using Elgato or potentially Ocelote, say if you need a GPU or something like that. Okay. So what do you do once you have an interactive job? Any ideas? So you have access to all of the compute nodes. We talked about what the compute nodes can do and what they have access to. So What would you try to do once you have an interactive session? Yeah, run a calculation or debug. So yeah, interactive jobs are great for debugging because you get real-time feedback, and you don't have to wait for the batch job to process through the queue and then look at the output logs. That debugging through batch jobs is a little bit more of a pain, but debugging through interactive jobs is very straightforward. So you can load your modules, you can compile software, you can run your scripts, you can do testing, debugging, and any number of things. So interactive jobs, the world is your oyster. You can do anything you like. But what happens if my internet cuts out during an interactive session? Say, sometimes the internet just glitches and it cuts out for a second. What would happen to my interactive session? No, it actually won't be fine. If the internet cuts out for a second, that means I'll be disconnected from the HPC and the interactive session will end. So any code that I may have been running in that interactive session will be terminated. So that is one downside of using the interactive sessions. So also, for example, if I forget that I have a terminal open running code on the HPC through an interactive session and I shut my laptop and walk out the door, that will also terminate the code. Yes, so it is dissimilar from starting a job and being able to leave. So that's one downside of interactive sessions. If you get disconnected, it will terminate. And in addition, SSH connections do have timeouts. So it is possible that even if I don't have any internet issues, and even if I do leave my laptop open, it is possible that the SSH connection will be terminated because it hasn't received any input and the code will be terminated. So question from Guillermo, screen. So yes, screen would keep the session running while you are away. And another important caveat from Devin, if you are using Open On Demand to do some type of graphical application, such as a Jupyter notebook, if you do get disconnected, that session is still running. So this is an important distinction between the terminal interactive session and those jobs that you can run on Open On Demand. So if I have a Jupyter notebook or something else running through Open On Demand and I did get disconnected or I close my laptop, that session will still be fine and I can resume that once I gain an internet connection again. However, the interactive session through the terminal will be terminated. So how can I run longer jobs without fear of losing my work? The answer here is batch jobs. So finally, we're talking about batch jobs. Set and forget computing. You write a script with your resource request and your job commands. You send that script to the scheduler and you log off and wait. And then it'll run whenever the scheduler decides that it should run. So this is a good way of running a large number of jobs or running jobs that will take a long time that you don't want to have to babysit while they're running. Batch jobs are highly flexible in what you can do with them. So as an overview, batch jobs are a way to run code automatically without user oversight or even an active connection to the HPC. Once you have submitted that job, it will proceed automatically. Just like all other job types, batch jobs are allocated compute resources, and you do that through the task scheduler known as Slurm. Unlike other job types, batch jobs require a batch script that determines everything the job will do in advance. So with an interactive session, you're able to, give it commands, change what you're doing on the fly. With a batch job, you type in all of your commands into a script in advance, and then that script gets run. So The batch script is submitted by using the sbatch command, and then you type in the name of your script, and it will proceed through the queue automatically once you have submitted that command. Okay. So let's look at an example of a batch script. So here is a basic, simple batch script for illustration purposes. Let's go through each of the sections. So the top section here in blue, this is called the shebang, the hashtag !bin/bash. That just tells the system that this is a bash script, and it tells it how to interpret it. Then we go through the directive section, where this is the resource request. So you can see here that I'm indicating that I want the standard partition. I've put the name of my group here. I've given it one node. I've given it one task, and I've given it 1 minute of time. So this is just an example. You might want to increase those numbers for a real job. And then lastly, down here, we have the code section that tells the computer what to do during the job. So the first thing that you see there is module load Python /3.9. So if you do need to load any software, you'll probably want to do that at the top of your code section. You can put in any bash commands that you like. So if I want to change directory, I can do that with the cd command. And then I can execute my Python by typing Python3 and the command that I want. And then here, that sleep is just used for demonstration purposes. So this is an example of a batch script. There are quite a lot of options that you can put in the directive section. So I definitely recommend checking out our documentation or the official Slurm documentation on what are the options that you can put there. So you can put things like error logs or output logs. You can have it email you when the job starts. There's a lot of different things that you can do there. So let's go through some basic Slurm commands that you can use while you're on the system. So the sbatch command, as we just saw, submits your batch script. You can use the sq command to see jobs that are pending or waiting to run, or jobs that are currently running. And there are options that you can pass to the sq command to make it a little bit easier to read, because if you just go to the HPC and type in sq, you're going to see every job that's waiting, and that's going to be probably too many to really run through or look through. I see a question in the chat here from Dave. It says, how does the batch script know which compute node to use or resources to pull from? Do you have to type sbatch command for the script when you are on the proper compute node? No, the sbatch command gets submitted from the login node. The one thing that does change is you'll need to be sure that you're on the right cluster. So Puma, Ocelote, or Elgato, the job will get submitted only to that particular cluster that you're actively on. But in terms of how does the batch script know which compute nodes to use? So Slurm is the task scheduling program. So Slurm has a list of all of the jobs that are running on all of the different compute nodes and what order they're going to run in. And it will determine which compute node to use that matches your resource request that fits well within the time slot. So there's a whole big program called Slurm that operates behind the scenes. So you don't have to think about which particular node to submit to. It will match whatever resource request that you give it. And then one more question here from Martin. It says sbatch -- time. What if I don't know how long it will take? What if my job runs out of time but isn't finished? Great question. If your job runs out of time but isn't finished, it depends on what exactly you're running. If you have, you know, if you're saving your data as you're running the program, then that data will be saved. However, if you're waiting until the program is finished to save your data, unfortunately, you might lose your work. So in this case, the answer, unfortunately, is basically just guess. If you put in longer time, it might take a little bit longer to get through the queue. But if you underestimate, then you might lose your work. So it's kind of a process of testing. So you can estimate how much time you might need and then maybe slightly overestimate it to make sure that you don't run out of time. Jose has a question. I like to do an interactive session and run a small portion of the job to see how long that takes and use that to scale the whole job. Yeah, that's a great example of how to test the time it might take. Another great question from Miriam. What if the job runs faster than the allocated time? Do we still have to pay for the entire requested amount of time? No, you only pay for the time that you use. So if I request 24 hours for my job, and then my job completes in 20 hours, those 4 hours get refunded back to my account. But they only get refunded back once the job has completed. So great questions. Only have a few minutes left, so let's run through these Slurm commands. So saccount is a way to see previous jobs that have completed or failed. salloc is so that interactive command that we discussed earlier is actually a wrapper for the salloc command. So if you want a little bit more control over your interactive session, you can look up this command and the options that it can take. scontrol is a way to get info on jobs. And if I ran a job, but I decided that, oops, never mind, I wanted to change something, I can use scancel and the job ID to cancel that job, and then maybe resubmit it later with sbatch. So interactive versus batch jobs. We'll just go through this real quick. The resources for an interactive job are described in the command itself, and you can input and commands and receive output in real time. And the job is canceled if the connection is lost. Batch jobs, on the other hand, are requested with sbatch. They require a batch script, save to output files, and run without supervision or active connection. And both use Slurm. Both can use whatever compute resources you request from it, and they have access to all of the partitions and wait times and all of that stuff. Use cases, we did kind of discuss those as we were going. So it's just, I have this activity in here. Let's just talk about it. We don't have to actually go through and do it. Writing a basic Python script and then submitting it to the queue. So this is your overview of what it's going to look like. You write the script, you write a batch script, and then you submit the batch script. So you can write anything you want. It can be as simple as, print hello world. Here's the overview of what you're going to do. Log in, create your file, edit the script to include any commands that you want, and then save it. Once you've saved it, you create your batch script, and I have a few extra options in here that we didn't see before, such as output and error. Load your modules, call your command. We saw this in the previous batch script, and then submit. Send it to the scheduler. sbatch myscript.slurm. Check the queue. You can use the -- user flag to see only your jobs, and then you can view the output files by the cat command there just dumps all of the contents of the file. So name.out, name.error. And check the job history report. So you can use the job history command to see things like how much resources it used, what directory it was submitted from, how long it ran for. There's a lot of information in that job history command. All right, and that's it. Here is the information that you'll need to contact us. The documentation is docs.hpc.arizona.edu. If you want to contact us, you can use the ServiceNow portal, HPC support and consulting. And if you want to drop by and talk to us about anything that might be going on, every Wednesday, 2 to 4 p.m. on GatherTown. So that's a link. The slides are provided. And thank you for listening, everybody.
Thank you so much, Ethan. That was a really thorough and incredibly interactive talk. Thank you for that. And thank you to everybody in the audience for participating and asking questions. And we really appreciate all of this engagement. Let's take these 2 minutes and get our next speaker all set up for today.